So greetings to you all. Today we have a guest speaker, Dr. Benedikt Riedel. He is a computing manager for the IceCube Neutrino Observatory, which is at University of Wisconsin-Madison. He's also the Heterogeneous Systems Lead for the Accelerated AI Algorithms for Data-Driven Discovery. We're also honored to have him as a member of our Pan-HDR IceMelt Community Council, which you can see on our iHub website. So thank you so much, Dr. Riedel, for joining us today, and we're excited to hear your talk titled IceCube, Science and Computing. Please take it away. Thank you.
Sure. Sorry about the slight technical glitch there. So let's get started about sort of what IceCube is. IceCube is currently an operational neutrino telescope. What do we mean by that? It's kind of a little weird in terms of thinking about telescope and observatory. Rather than sort of having a traditional dome or CCD to observe the night sky, we look for something called neutrinos, and I will go into why exactly we do that in a little bit. But what IceCube is basically a large neutrino detector that we built into the south polar ice. We mainly picked the location because A, there's infrastructure, and B, we have an abundance of abundance of ice there, about 2.5 kilometers worth, that we could deploy a detector into. And the other big portion of the other big piece there is that the ice is very clear from, as most of you know, from millennia of deposition and pressure. Basically, the ice is a very clear medium, some of the clearest medium that we have on Earth. And what we did was we basically drilled into the ice sheet and then deployed what we call a digital optical module, or DOM, into them. They're basically a basic basketball-sized light detector plus a readout electronics for set detector that are then deployed in these holes, and basically look for light sources, and how this all works, I'll explain in a minute. Sort of overall, sort of IceCube overall is a very novel instrument. It's not just your classical particle physics experiment. It is, it goes well beyond that. So there's a large astrophysics component, but there's also neutrino physics, particle physics, earth science component as well. And then, of course, searches for unknown particles or unknown, or rather theoretical particles that are outside our current understanding or have only been predicted in theory. And across this, you kind of see, that there is there's a broad science, but there's also sort of lots of needs, or a lot of needs in terms of how you process that data, and also we do a lot of simulations, and I will explain in a second also why we do a lot of simulations. So why overall do this? So in classical astronomy, you typically use some form of light, so microwaves, optical is sort of and gamma rays are kind of sort of the ones that we hear about every day. But there's about 20% of the universe that is dark in those what we call messengers, or sort of probes in that sense. So you have about 80% of the universe that's observable, and about 20% that we have no idea what was actually there. And then we need a new form of science to really probe that 20% of the universe that is quote unquote dark to traditional astronomy. And there's really, as far as we know, there's really only two sets of messengers that can help us with this. One is gravitational waves, which our colleagues over at the Large Interferometric Gravitational Wave Observatory, or LIGO, are doing. And then there's neutrinos, which is what IceCube is doing right now. So basically, we're trying to probe about 20% of the universe that have not been probed before. A quick history lesson and how why we're doing this in Antarctica. So this whole thing is the whole idea is nearly it's over 35 years old. It's over 35 years old. So it started in 1988 with RPI, who had this idea, who came up with this idea. Then in 2000 we had our predecessor experiment called Amanda. And with this experiment, we were basically able to, it was a proof of concept to first order that, you can actually build a detector in the ice and operate it. And then, of course, there's also the R&D aspect of it. You were able to show that, you can actually do this. With that knowledge, we then went out 10 years later and built IceCube over the next few years, over nearly a 6-year period. And in 2013, we kind of had our first discovery, which was astrophysical neutrinos. So in this case, high energy astrophysical neutrinos. And then from there on out, we had our sort of the sort of plethora of other sources that we discovered. And then also in 2021, sort of our first particle physics discovery at extremely high energies. And this is the glacial resonance. So this means that we were able to probe some fundamental physics that was not done before on Earth, and can't be done on Earth, considering the energies that are involved here. And then we proceeded, throughout the last couple of years to basically create more, start creating catalogs of sources. So we're kind of going from the discovery phase now into the precision physics phase, or precision measurement phase. So why do I mention simulation? So the big thing here is sort of what I like to call the standard model of particle physics analysis. We kind of we have a theory of some theoretical theory. We then take that theory and basically simulate, to the best of our knowledge, how our detector would respond to said theory. So certain particles or certain things like that. And then from there, we get sort of a prospective readout or a prospective simulated data. And we take that simulated data and then compare it to what we actually observe in the detector. And then from there, we can kind of compare and contrast and say, well, given this theory of for example, the rate of astrophysical neutrinos, and we detect this means that there's something else going on, or something is incomplete in our theory, and then this sort of cycle continues. As we hone our theories, we change our simulations and then compare that to our data again, and sort of this cycle continues. Sort of, for example, what IceCube actually observes in the grand scheme of things can be categorized in sort of 3 broad buckets. One is what we call a track. It's basically you have sort of a line through the detector. You can see this here in the diagram. And then we have something called a cascade, or you can call it a ball. Or you have a double bang or a dumbbell. So these various different shapes are indicators of different physical processes that happen in the detector, and basically provide us different pieces of the detector. So, for example, the track has a very good pointing resolution, meaning we can very easily trace back to the origin. The cascade has very good energy resolution, so meaning we can measure the energy of the involved particles very well, and the dumbbell kind of has both, but we've never actually observed the dumbbell. This is a theoretical observation that is another sort of would be the next big thing for us. Just to sort of demonstrate the scale of IceCube in some respects. So this is, if you've ever been to Madison, this is a picture of the union and sort of the libraries, and you can see how big the events are. These are sort of one-to-one scale in that case. So, these events are hundreds of, hundreds, if not thousands, hundreds of meters in size in both, in all three directions. So basically, you're really talking about, you can also see the scale of the detector. So you're talking about a cubic kilometer here. So we're actually also building an extension to IceCube called the IceCube Upgrade, and we also have a proposal, or rather a projection in for something called IceCube Gen 2. But I'll focus on the upgrade right now because that's currently under construction. And the upgrade is basically us putting what we call an infill. So basically, we're again doing R&D for new detectors for IceCube Gen 2, but we're also wanting to probe lower in energies. So we're putting the detectors closer together and with tighter spacing between them and different detectors overall, so that we have much better resolution or much better or much more information at lower energies. This is especially crucial for our calibration. I'll go into that, why exactly that is needed. And then also, as I said, this is R&D for IceCube Gen 2, which basically is an extension of IceCube to make it 8 times larger than it is right now. So just to show what the upgrade does in terms of our information density, you can see on the left is sort of a current event and how sparse the information is versus the upgrade, where you can see how that event is. We have a lot more information about it, and we can therefore do better science with it. Of course, with more information equals more ability to really constrain and reconstruct some of the features of that event. And one of the big things in IceCube science is multi-messenger astrophysics. This is sort of a fairly new field within physics or within astrophysics or astronomy. It's a very much an overlap between physics and astronomy. And basically what we're trying to do is we're trying to observe astrophysical phenomena, whatever they are, with more than one messenger. And messenger here is, as I mentioned before, are gravitational waves, neutrinos, or electromagnetic emission, or what we would classically call light. It's one of NSF's Big 10 ideas, similar to the northern. I think there's the navigating the northern oceans is one of the other ones, and this has been done basically with gravitational waves and electromagnetic emission, and then also neutrinos and electromagnetic emission. So there's this event from an astrophysical source called the Blazer TXS 0506. And basically what happened was we first detected a neutrino that had a very good, or we detected a particle from this, or a neutrino from this source. And then we basically went out to the community and said, we detected this, please follow up. And within about a month, a series of multiple telescopes across the electromagnetic spectrum was able to basically confirm that this object, or the source in the sky, was flaring, meaning that it was going through some kind of change process, and was really bright in the sky across neutrinos and then also the electromagnetic spectrum. And so basically what this boils down to is that we've opened up our sky basically to a new way of looking at it. And we have done this with our own galaxy as well, and I'll go into that in a second. Basically, we can observe the sky now, or point at individual sources that we know about and find neutrinos from them, and then detect them in IceCube. Just sort of the one of the computing challenges, one of the challenges with all of this is the data. So we have a neutrino coming in, we have all the data that is generated at the South Pole, but as you might imagine, the South Pole is isolated. It doesn't have, you know, your gigabit ether. It doesn't have your gigabit Ethernet or anything. It's very it doesn't even have Starlink at this point. It is very isolated. So we send our data over 3 different streams, where we have an alert stream basically that goes over an Iridium satellite phone. Then we have something called TDRS, which NSF and NASA sort of share in some respects, that basically can send a reduced data set, you know, once a day or a couple times a day, depending on the satellite window. And then once a year, you know, during the austral summer, we can actually retrieve our data in forms of disks, and then that gets shipped back to Madison. And all this data basically gets back to Madison. And especially if our alert data, we then do some initial processing on it, or some decision making on it, and then send it out to our partners to basically say, you know, we found something interesting from this location in the sky. Have you guys seen anything else? And I mean, this is really a large coordinated effort between, you know, IceCube, LIGO, and multiple you know, hundreds of different astronomical observatories that can potentially follow these up, depending on where they are in the world and what time it was. So there's a very large community that basically has the potential to follow up to whatever IceCube sees, and vice versa. You're now looking at basically reversing this and saying, you know, LIGO has seen something, or one of our colleagues in the in astronomy has seen something, and then we follow up on it and look in our data to see, do we see something weird or unusual rather from that source. So, but besides itself, so for example, what IceCube has done so far in terms of that is also we've opened up a new view of our galaxy. So you might have seen some of these pictures before, where you know, there's an optical view. You see it at night sometimes. In the southern hemisphere, you'll see it more prominently, but you'll see it in the northern hemisphere. You'll see the arms of our galaxy, and then we can do this also in gamma rays. So you'll have a completely different picture, and also in other ones. And what IceCube has done is basically we have done this in neutrinos, meaning we have a completely new view of our galaxy in terms of you know, an astronomical thing. One of the key things here to note is that, you know, this is driven by machine learning, or sort of a hybrid machine learning combined with a traditional approach, to be able to actually perform this analysis, and then also have the resolution or the means to basically go through the data at that precision. So one of the big things in IceCube is GPUs, and as you can imagine, also with machine learning. But we've been doing this for over a decade, over a dozen years now. And the reason is that IceCube is basically, you know, we dropped a high precision instrument into sort of a natural medium, meaning, you know, we didn't know necessarily, you know, if there will. For example, we see volcanic activity from a few million years ago, or a few 100,000 years ago, in the ice sheet in the detector. And that, you know, those aspects, because the ice has been deployed, or rather deposited, over so many millennia, it is not uniform. It is not ideal necessarily. It's not a man-made medium, so we can't really, you know, characterize it a priori. So we need to have a brute force approach to kind of characterize this, and we use GPUs to do ray tracing for this. So basically, we have emissions of light in a detector as we are, and then we have to brute force kind of the ray tracing of that to the best of our knowledge of the detector through calibration data. And sort of to exemplify this, this is an example of a particle that travels, that's traveling and giving off light as it travels through the ice. And then each of these little sort of filaments is an individual particle of light or photon as it travels through the light. And you can see, you know, how diffuse this is as it travels through the detector. And then we detect, you know, individual filaments, maybe, you know, hundreds, maybe a couple thousand out of this large thing. But we have to be able to do these simulations. We have to be able to trace these through the ice to the best of our knowledge. And we use GPUs for that. Sort of to reiterate a little bit, sort of the ice model and its natural tendency. So, for example, roughly every year, or maybe every 2 years, we get a new calibration data. We get more calibration data, and then, you know, very smart people go off and take that data and derive a new what we call an ice model. So basically, the optical properties of the ice. And if you were to do this by yourself, you know, fitting or basically deriving this model from all the data that we have takes roughly 400 GPU years, give or take. And of course, you know, these analyses can vary, and this natural medium, since it's basically our detector, makes it very much sort of a key piece to defining how we see things. The big thing is one of the big things we have recently found is something called birefringence, and that basically has to do with the flow of the flow of the glacier as it crosses the bedrock, and of course the bedrock itself is also not even or a plane, rather it has hills and valleys. And as the ice does that, the ice layers are basically that were deposited are compressed and extended. And there is a sort of how should I put this, a natural tendency for the ice to be clearer in certain directions than it is in other directions. And that's because of the polycrystal nature of the ice. And then this effect of the motion over the bedrock and how that exactly arranges the ice crystals. And so what happens is that, you know, as you can see from this sort of cartoon, is that an emission or sort of a source that you would expect to have a spherical or symmetric emission in all three directions becomes shifted considerably, especially along the axis of the ice flow, meaning that you see how, for example, it is brighter in one direction. We have more information in one direction versus the other because there's a preferential direction for the light to go, or rather, there's a less opaqueness in certain directions because of this. And that has really been important to us to make some of these discoveries and understand, you know, how our detector actually works and how we do things in terms of our science, and that is one big key piece. So I'm going to shift a little bit to how we do computing in IceCube, just to sort of bring it back a little bit to the sort of harnessing the data revolution piece. IceCube in and of itself is sort of classical particle physics computing. It's what some people call embarrassingly parallel, or ingeniously parallelizable. Basically, we use grid computing. We have these very well-defined periods of interest that we operate on when we call events. They're basically readout windows, and we have you know, we have sort of chunks of time that we take pictures. It's basically a picture or a small movie that we take every we take at about roughly 3,000 hertz. And then we have many channels. Again, we have 5,000 detectors, but not everyone is involved in every one of these detectors. Then, of course, ideally you would compute on a per event basis, similar, you would in sort of you would like to compute on a per image basis or on a per readout basis. As I said, the detector itself has no continual uplink, or basically we're kind of cut off from the detector's cut off from the world for most of the year. We have these extreme environments, the Antarctica, or especially the South Pole, is roughly minus 40 C's is a warm day. It's a desert, so there's for computing equipment, that's also an issue. We require GPUs for our simulation, and we do a lot of our software in-house because of these special requirements, and of course the special that we are, the first experiment to do this at these energies, across these energies, across this large swath of this night sky. So it's really, we're not very specialized or very broad in our searches. And of course, that brings us that we have a very hard time predicting what a single computing or unit of compute does, or what a single job or things like that does. It is very much hard to predict at that point. That makes it difficult for sort of from a computer science point of view. So just zooming in a little bit, from Madison, so where we run IceCube management operations, we basically tie together what we call a grid or a global pool of resources that are mostly shared and opportunistic. So the majority of the resources that IceCube uses are not owned by IceCube. We basically borrow and most of our resources. And of course, this is changing, but we typically have an atypical requirement. Mostly the GPUs were a big thing. Then we also have very high uptime. We've been basically on for the last 12 years continuously. We have somewhere around 99% uptime since the detector has started data taking in 2011. And then also science has changed a lot over the last 12 years, especially, machine learning is one big thing, but multi-parameter astrophysics and the time constraints that come with that are somewhat of a novelty for us, and of course bring a whole different requirement to the entire enterprise. So one of these things, sort of going back to multi-parameter astrophysics and how we do reconstruction from like sort of a computing point of view. So what we do is basically we have this data set and now want to determine the direction of these events or this detection. And the most accurate thing to do, or rather, not necessarily most accurate, but most sort of precise, accurate, depending on who you ask, is to basically test different points on the sky and determine, is this a good point for this detection to come from, and then testing that across the sky. So basically, what we do is we take the sky and we parcel it up. We do a coarse grain, basically a scan across the sky, and then we kind of hone in on a very specific we hone in on the point we believe is the origin of this event or this particle, this detection. So and the big thing here is, we create then these maps. So this is only a zoomed in map. So this is, very much, you can see the individual pixels. Each of these pixels is being tested, and we have to test each of these pixels because from our given from our experience, we know that a single detection could yield a new way of looking at the universe, but also it can tell us something about the source or the objects that are close by. So for example, here there's 3 potential sources that are close by to this event, but but they're, outside of, the standard bounds, I would say, and or the bounds that we have defined as important for IceCube. And then as you can see, it is that from an astronomy point of view, this is, massive amounts of space and talking about degrees on the sky. But, for sort of a fledgling science like ours, this is really important to really hone down and hone in on these individual pointings. So all of this requires a massive amount of computation, and sort of one big thing, that we have done is in concert with these San Diego Supercomputing Center is what we call the cloudburst experiment. So there's always a big question with an IceCube and with science in general. Is the cloud worth it? Can we use the cloud? And all its sort of ill-defined, if I go to AWS, I can get all the resources I ever needed. But ultimately, the question there is not necessarily, yes, I can get all the resources that I need, but can I actually harness them? There's a big divide between giving somebody a credit card and then saying how can I actually use this new tool that you've given me, that I've paid for. And so the original plan was to basically create what we call an exaflop compute pool. So this was 2019. And so Frontier and Aurora were still in the building or the construction phase, and basically we wanted to be like, you can do this exaflop computing pool in the cloud, not necessarily at tightly interconnected, but you can actually harness 80,000 at that point, and maybe 100s. And basically what we're able to show is we had 3 different experiments. And the first 2 are kind of the most important ones, where, in the first experiment, we just bought everything that we could across the world, across all the 3 big cloud providers. And we were able to get, 51,000 GPUs for roughly 2 hours, which basically gives us, at the time, about 90% of the largest supercomputer at the time. I mean, this was done in concert with the cloud providers. So basically, we talked to them and got, you should do it at this time, since they have better knowledge of their usage. And also, a sense of how much this would cost ultimately. How much does 2 hours on Summit cost if I were to go to some other place? And then the second experiment, which is the more realistic one, is basically saying, let's be the most let's extend the goal. Let's be cost effective, and how much computing can we get in an 8-hour, normal day, working day, and how much would that cost us? And then here we achieved an exaflop hour, meaning we got 1 hour of Frontier basically for in an 8-hour period across the world, of course, distributed for about $60,000. Just to kind of drive home what this means in terms of aggregating resources. All these plots, these different colors are different regions. So you can see this is not just one region. This is all the regions combined, or all the available regions that had GPUs. So we had 28 total regions distributed across the globe that participated in this. And you can see that the cloud is not a sort of a uniform or homogeneous entity. It is really multiple mini clouds that are distributed across the world, and you have to then orchestrate that. So there is a sort of a very big overhead ahead of saying, I want to do this computing in the cloud. That is one statement, but the other, there's a very big sort of learning curve and a very big infrastructure curve that you need to participate or rather accommodate for. Sort of looking under the hood, how do we actually do this? From a particle or from sort of a distributed high throughput computing point of view, or rather sort of particle physics point of view, it's very well-known technology at this point. Basically, we created our mini clouds in each region, and then we basically aggregated all of that together in sort of a mega cloud, and then and the big piece here is also data movement. Is, you know, how do we move the data in and out, and then also how do we move the data back and forth, and we changed it up a little bit between the different experiments. In the first experiment, we've stored everything in the cloud, basically saying, you know, let the cloud, we don't want to deal with any networks or any network latency. Rather, we store the data next to the compute. And in the second was basically we pulled all the data out of UW. So basically we maxed out the network usage from UW into the cloud for that day. And then we stored the output in the cloud just to sort of have one directional thing. Sort of a little bit on the IceCube simulation workflow and how that actually works. So as you can imagine, simulating a detector that's a cubic kilometer in size is not easy. And so we go through basically 4 major steps and move a lot of data around in the meantime. We move about 175 petabytes a day, mostly in simulation data and mostly in intermediary data. Basically, we always ship data back and forth from where it was generated to Madison and then ship it back out for the next step. This is somewhat inefficient, but we don't have the, or should I say, we don't have the global reach of the LHC or other large particle physics experiments, so we mostly have to, you know, build our infrastructure around this. So we always have sort of a central data warehouse in Madison that is really taking, that does a lot of data movement, a lot of data, sort of intermediary data storage for us. One other thing that we've developed in around is sort of like this idea of, you know, use technology that is available and tested, and as an expert at doing a certain task, sort of specialize the software. This is very much sort of a Unix principle. And what we built is basically what we call PyGliden, which allows us to aggregate resources across the globe, as I've shown before, but using HD Condor in a very simple web server. Basically, the remote site just queries a web server and then submits a pseudo job that connects back to our pool, and then we can get a large computing pool. We usually have around 20 to 30,000 potential targets at any given time. So now switching gears a little bit again with going into AI and things like that, and a little bit of context here, sort of the AI training. One of the big things here is that's also a big topic in A3D3 is AI and AI inference and AI training. The big thing for us is, you know, at this point, a similar ML training resource, so a simple, you know, 8 GPU box is anywhere from a quarter to $500,000, depending on who you ask. And then it's simple that, you know, us as an experiment, and I'm assuming this is the same thing in iHarp, is that we can't necessarily afford that. We don't necessarily have, we have a lot of competition at this point we don't necessarily have nobody so far has said we need this. There's one student came to me on Monday and was like, well, I need this. And I'm like, well, I can't justify, you know, $250,000 purchase on one student. So it's really difficult for us to kind of gauge the need or demand for AI compared to you know, our financial constraints. The other big thing is AI inference. There's sort of data streaming. So we do have basically continuous data stream. So we could stream, or we build data pipelines that are more sort of incremental. And a big thing also is maximizing the GPU usage for inference. I mean, this is one of the big things that we've noticed, especially also with ray tracing, is that using a GPU to its fullest capacity is difficult. So there are services and methods that especially have come out of A3D3 to maximize the GPU utilization. And then the other 3 points are mostly to deal with sort of if you're running your own infrastructure and how exactly you want to move this. So I'll just skip over these and for the sake of time. And then so from the AI side, there's multiple different applications here. So there's identification. So as I said, we have different geometric shapes for our events, and but then from there we can even go drill a little deeper. So these events were produced by different physical phenomenon. They are both aligned, but they look very different in terms of their sort of their energy deposition in the detector and what that exactly means. So there's sort of subtle differences that can help us identify these particles much better and then provide us a much better, deeper insight. So currently we have CNNs that do this, but we're looking also at graph neural networks and transformers as an option to really drive this. Similarly, I've mentioned this before that these events, these dumbbell events, you want to call them, they're extremely rare. I mean, we would expect one every decade roughly, but we haven't detected one yet. I mean, if you look at statistics, one every decade, not discovering it is not that much of a thing. But what happens is that because at that point the detector is too big again, what happens is at lower energies these two kind of meld together and they become one large. They become this ball shape, and actually you can you could potentially differentiate them in how our detector readouts look. So you have sort of one peak versus a double peak in a single detector. And recently we used the CNN to basically determine these subtle changes in basically you made pictures of the detector and determine subtle changes in these readouts to be able to see that there are 7 candidate events that show this information and that we have seen these events, but only as these single spherical structures. One of the big things you might have seen, might have understood by now is what we call reconstruction, or sort of determining direction, the energy and the type of a detector. So again, we use maximum likelihood techniques right now for the most part that cannot support all the detector knowledge that we have, but they are really sort of our bread and butter to first extent because they are very statistically robust and we understand them. There's also the issue with AI models that we are very cognizant of errors in our things. We need a pointing error, so we want to know it's pointing in this direction, and the error around that location is very important to us. But as you might know, AI is not very good at giving you an error necessarily, or a well understood error, statistically speaking. So that is one of the big things here that we're looking at. But if you do use AI and you compare it a priori to our existing things, the one big thing is sort of like square peg in the round hole kind of issue that the IceCube is not a CCD. It has an irregular geometry, so you need to do some data some data munching and some data reorientation to drill down some of these aspects. But ultimately what happens is if you use a CNN, you have a much better runtime per event. So you save significant amount of compute time, depending on what you save a significant amount of time per event. Oops, sorry. and also the overall the mean or the spread along the for those reconstructions is a lot tighter, so that you get a lot better results, or faster resolution and better resolution to first order than our standard methods. So this is really promising and really something that we're investing a lot of things into. Sort of going back on this a little bit, the issue really is that in the maximum likelihood technique, we cannot parameterize all the various things that are happening in the detector as a PDF or in this PDF or a likelihood function. Ultimately, there's a lot of complexity in the detector and with detector details and the physics of all of this that you don't necessarily get that you cannot analytically or you cannot write down necessarily, or you cannot parameterize well. And that is really a shortcoming of the maximum likelihood technique. But if you use a generator or a neural network with a gradient descent minimizer and things like that, you can actually take out some of these. You can parameterize more of the detector pieces, because ultimately an AI model is just a function approximator, a very good function approximator. And so we use this to basically replace our PDFs with sort of a functionally approximate PDF. Ultimately, sort of quickly, the big thing in IceCube is also simulation. We do a lot of simulation. We use a lot of compute time to do simulation because of how sort of the standard model of particle physics analysis works. And the issue is, of course, that we have an enormously high uptime. We've been operating for over a decade. We are talking about 500. Basically, where we're talking about orders of magnitude more compute than we could consume easily. The positive thing, though, is that a lot of the physics that derives here is actually graph-based. So basically, you have this is all a graph ultimately, or actually a DAG, and directed acyclical graph. So basically, it's a unidirectional graph. And and knowing this, we should be able to parameterize all of these details using GNNs or other AI methods to really accelerate our simulation, and then ultimately get out to these goals that we have, and hopefully be more basically accelerate our simulation and get to the goals that we've kind of set for ourselves. So I want to thank you for your attention, and I'm happy to answer any questions.
Thank you, Dr. Riedel. So we have a couple of questions passed in the chat, and if these questions were answered as I was speaking, please feel free to share. But if you see the chat we have from Dr. Riedel, she's asking, to what extent has a multi-messenger astrophysics been supported by automated workflows to identify patterns, trends, or anomalies in big data?
Sorry, I didn't hear the middle part.
So to what extent has the multi-messenger astrophysics been supported by automated workflows to identify patterns, trends, or anomalies in the big data?
Very, very little at this point. There are some automated astronomical observatories that they're completely automated. They have like a campaign, but if an alert came in, they would reposition themselves immediately but really the automation of multi-messenger astrophysics is still in its infancy. We do send out alerts automatically, but what happens on the other end in the in the astronomy community or in the gravitational wave community is very much up to the individual experiments or observatories at that point. So they also have automated, some have automated, like LIGO has an automated scheme similar, where they detect something, they send out the alert, and then it's sort of like it's in the world, and then how people respond is really not necessarily 100% automated. There are some efforts between NSF and NASA to provide better communication and better automation, but I mean these are still, I would say at least a couple years, if not 5 years away from really being 100% automated.
Okay. I hope that answered your question, Dr. Riedel. We also have another question from a student, Malloy. He's wondering, have you used transfer learning for new data for reducing the computational cost?
Yeah, we're currently looking at transformers. I mean, there's sort of a...
basically, can I add more, Dr. Riedel?
Sure.
My question is, it seems to me that when new data comes, you want to train the model from scratch, like more GPU, more data in the number 16 slide. So my, just my curious mind, have you used any transfer learning method, so that we do not need to start learning from, we do not need to train the model from scratch? It will reduce some competition, right? Because if there is some data.
We haven't really used transfer learning, just because, I mean, I know some people have tried things like pre-trained, like Resident 50 and the like to as a benchmark, but they've always found that going with your own is kind of or defining your own has always been better, or has always performed better than the sort of pre-trained models. And then that might change with transformers and how exactly you can operate them. So for example, you could, for example, if you do in LLMs or in large language models, where you have sort of a base model and then you build one on top of that. That's something that we haven't really looked at, and I think that's kind of where we're going in some respects.
Can I ask you another question, Dr. Riedel?
Sure.
Just you have talked about the graph neural network for applying this. So my question is the graph building methods here, it will be a heterogeneous graph or homogeneous graph, because a lot of parameters, physics parameters is here. Like I have seen pi, Neutrino, a lot of things. So it will be a heterogeneous graph or homogeneous graph? Can you let me know?
It will be a heterogeneous graph, but we are looking at some of this. We're actually thinking we're starting. We haven't fully experimented with it, but we're thinking more about it as in terms of a sentence than a graph, just because it ultimately is like a sentence. I mean, you can argue that a transformer is just a souped up GNN in some respects. And similarly here, I think we will find more luck with transformers than we will with GNNs, just because of the computational cost of building the graph is very, very expensive.
Yes, that's also come in my mind, that it may be like computationally heavy also building the graph, because a lot of heterogeneous parameters also I am seeing. Although I have not sound knowledge about physics, but a lot of parameters I have seen.
Thanks, Mullah. I just want to make sure if others have questions. I also have some questions, but
okay. Sorry.
No, Mullah, all good questions. Thank you.
Okay, thank you.
If I can jump in with a question as well, I was a little bit selfish in jumping in. So really interesting talk, and the scale of it is just tremendous. It's really amazing, the scale of all of this. I have a few questions, but I'll try to at least highlight two of them. One is about the use and the impact. So this is something philosophical to some extent, that as you have more GPUs and more compute, it has a reverse sustainability impact, right? Because it needs cooling and energy and all of that kind of stuff. At this scale, which is really a massive scale, what could be the impacts on sustainability, environmental sustainability? That's one part. And the other question is the cost benefit of this, right? So as we add more GPUs, the link between the GPUs, the bridge between the GPUs also becomes expensive. And is the return on efficiency substantial to say that, you know, a higher number of bridges are acceptable in these types of environments?
So from a sustainability point of view, I mean, IceCube is not very good in that sense. I mean, the detector itself runs on a diesel generator, so you know, and then we use a lot of computing, you know, ultimately, and that is not to be sneezed at in terms of, you know, how much cooling and power that takes. We are, however, especially in Gen 2, looking very strongly at alternative power for the facility, so that in some sense, you know, in the summer this would be solar because, you know, 24/7 sunshine, and you know, ultimately that is, and then the winter is really the problem where, you know, we've tried wind turbines. There is a steady wind in Antarctica and it would power but ultimately the temperature is the issue where the grease of the wind turbine would freeze. So there's an effort to make this more, with the experiment itself, more sustainable, but ultimately with GPUs, I would say if we were to do the same thing with CPUs, I mean, the GPU usage for our ray tracing is about 200%, 200 times larger. The speed of it is about 200 times compared to a CPU. So if you just do it is at that point more energy efficient. That being said, you know, this is changing also with how GPUs and the GPUs that are being purchased by HPC centers, etc. You know, changes as more people do AI stuff, and you know, the recent investments that NSF has made. You know, you can see the trend towards very AI focused compute, and that really somewhat hurts us on the GPU side, because NVIDIA and all the vendors are basically, you know, they have a limited die space, so they take more and more die space for machine learning compared to, you know, just raw compute. So there's that piece. Overall, I'm a little torn on how AI it will be sustainable for us. Basically, we're upfronting the cost in terms of sustainability by training the network, and then the execution is quote unquote cheap. But as I mentioned, you know, keeping a GPU fed at 100% is also very difficult, or not very difficult, but it's difficult. It's not it's not something that you easily do, and that's something that we are aware of and we are working towards. Ultimately, I mean, this is something that we are aware of and that we are taking into consideration as we extend the facility, that we need to think about how to be more efficient in terms of our computing and our facility in general.
So these are important considerations too. If there is no other question, I had one more question, but I'll wait to see if others have questions too.
Can I go ahead?
Yeah, Rohan. Yeah, go on.
Good evening, Dr. Riedel. The thing is that I have a small question. So are you training your model on the simulated data or the raw data which you are receiving directly from the sensor?
We are training it on the simulation because otherwise we didn't have the a priori, the knowledge. We don't have a priori, we don't know how what the data means. So we need to simulate it and then feed that into the algorithm.
Okay, so I mean, then I mean if in a real-time data actually there are noise actually, so how you are simulating the noises in your simulation actually to train your model?
We have, so this is in here. We have a model of our noise, and we use that model then to inject that noise into the detector.
Okay. I see. I see. Okay. 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 And the thing is that, I mean, for the real-time application, you can think about the continual learning also. There is a
Yes.
that is very good for real-time applications, actually. That will help you in detecting if the new data comes by, it will help to incorporate that thing in your model. Thank you.
Maybe I'll do a quick follow-up. I know we're well over time, but just at the beginning, you had mentioned that there were environmental science implications in the project as well.
Yes.
If you could briefly mention something about that, that would be great.
So sure. I mean, it is. We can there's a couple different things. So ultimately, IceCube is a $300 million thermometer. We can observe the temperature in the upper atmosphere, or the density rather in the upper atmosphere, very precisely through our background rate. So that's one aspect. And then and from there we have mostly our sciences or historical information. So glaciology, we can tell you, depending on the depth of the detector, we can tell you, this happens. So for example, there is a very distinct layer of dust in the detector from a very volcanically active period. A few millennia ago. I don't remember the exact. And then, of course, you can also see other layering, let me put it this way, in how the weather changed historically. There's also some convolution there with how long the ice has been there. So there's some pressure changes, how that works. Changes how the ice looks, but ultimately, you can see you have sort of a history of the glacial deposition there. The other piece is Earth tomography. So how we operate usually is we use the Earth as a shield for most of our things. So we look for things going through the Earth into the detector, and vice versa. What you can do is basically you can say is, okay, assuming, making assumptions about, your rate and whatnot, you can figure out the layering in the Earth's mantle through that, or at least very coarsely. You can give you a hint of what the Earth is made of, or how dense it is rather, at different layers. This is similar. I mean, if you've heard about these folks that use cosmic rays to peer through the pyramids in Egypt, basically what you do is you take a particle detector and you go around the pyramid and you detect basically the bombardment of particles, but because of that you can see hollow and chambers and things like that in the pyramid. And similarly here, we use the bombardment of particles from the Earth to basically be able to show that the densities of the Earth are changing as you change your angle of detection.
Thank you. Thank you so much.
So if anyone has any other questions, they can send an email to Dr. Riedel directly. Thank you so much, Dr. Riedel, for your presentation. It was very enlightening, and for your time today.
You're welcome.
Thanks so much.
Okay, thank you. Have a good one, everyone.